Welcome! In this session, we'll be exploring an essential binary tree problem, lowest common ancestor of a binary tree. This problem is a great way to deepen your understanding of tree traversal and recursion. Let's dive in. In this problem, we are tasked with finding the lowest common ancestor, or LCA, of two nodes in a binary tree. The LCA is defined as the lowest node in the tree such that both nodes, P and Q, are descendants of this node. Importantly, a node is considered a descendant of itself, so if one of the nodes is an ancestor of the other, it can still be the LCA. The input to the problem consists of the root of the binary tree, and the two nodes P and Q for which we need to find the LCA. The output will be a single tree node that represents this lowest common ancestor. To better understand the problem, let's look at an example. Here, the binary tree is represented as 35162080074, with P equals 5 and Q equals 1. The tree visualization shows the root node 3, which has two children, 5 on the left and 1 on the right. The subtree rooted at 5 contains nodes 6, 2, 7, and 4, while the subtree rooted at 1 contains nodes 0 and 8. The output for this example is 3, because it is the lowest node in the tree that has both nodes 5 and 1 as descendants. Here's the explanation for why the output is 3. The nodes 5 and 1 are both direct descendants of the root node 3. Since 3 is the lowest node that satisfies this condition, it is the LCA. Now, let's consider another example with the same binary tree, but this time with P equals 5 and Q equals 4. The output for this case will differ because of the relationship between these two nodes. In this example, the output is 5. This is because the node 5 is itself an ancestor of node 4. Remember, a node is considered a descendant of itself, so the lowest common ancestor of 5 and 4 is simply 5. This highlights an important concept in this problem: a node can be both an ancestor and the LCA when the other node lies within its subtree. Now, let's consider one more example to solidify our understanding of the LCA in binary trees. Here, the binary tree is much simpler, with just two nodes. One is the root and 2 is its left child. The input specifies P equals 1 and Q equals 2. The output is 1, because 1 is the root of the tree and directly contains 2 as its descendant. Since it is the lowest node that includes both P and Q, the LCA is 1. This example demonstrates that the LCA can also be the root of the tree when one node is the parent of the other. There are a few key edge cases to keep in mind for this problem. If P is an ancestor of Q, the LCA will be P. Similarly, if Q is an ancestor of P, the LCA will be Q. For balanced binary trees, the solution will typically explore the subtree where both P and Q reside. However, for skewed binary trees, the traversal becomes more linear, as the tree structure dictates the path. Understanding these scenarios is crucial for crafting an efficient solution that works across all tree configurations. To approach this problem, let's consider a brute force method first. The intuition here is straightforward: we can find the paths from the root node to P and Q, then compare these paths to determine the last common node, which would be the lowest common ancestor. This process involves two steps. First, we perform two separate recursive traversals to build the paths to P and Q. Next, we compare these paths starting from the root, and as soon as the paths diverge, the last common node is identified as the LCA. While this method is conceptually simple, it has some clear drawbacks. The time complexity is O(n) for the two traversals, plus another O(h) for comparing the paths, where n is the total number of nodes and h is the height of the tree. Additionally, the space complexity is O(h) for both the recursion stack and the storage of the paths, resulting in a total space usage of O(h). The key issue with this approach is that it performs redundant work, as parts of the tree are traversed multiple times, and it also requires additional memory to store the paths. This makes it inefficient for larger trees. A more efficient solution is the optimized recursive approach, which cleverly utilizes the structure of the binary tree. Here's how it works: we begin at the root node and recursively explore the left and right subtrees. If we encounter either P or Q, we immediately return that node. Now, if both the left and right subtrees return non-null values, it means we've found P and Q in separate branches, making the current node their lowest common ancestor. On the other hand, if only one subtree returns a non-null value, we simply propagate that value upwards in the recursion. This method avoids the need to explicitly store paths, as the recursion itself keeps track of the traversal and aggregates results naturally. The base cases ensure correctness. If we reach a null node, we return null, and if we find P or Q, we return the node directly. The efficiency of this approach is evident in its time complexity of O(n), as each node is visited exactly once, and its space complexity of O(h), which is limited to the recursion stack. The simplicity and elegance of this method make it a powerful solution. Now, an alternative to recursion is the iterative approach, which simulates the recursion stack using an explicit stack. In this method, we perform a depth-first traversal while maintaining a map of parent pointers for all nodes. Once we locate both P and Q, we can trace their paths back to the root using these parent pointers and identify the lowest common ancestor. While this approach has the same time complexity of O(n) for the traversal, its space complexity is higher at O(n) due to the additional memory required for the parent map and stack. Furthermore, it's less intuitive compared to the recursive method, as it involves additional bookkeeping. Considering the trade-offs, the optimized recursive approach is the chosen strategy. It stands out for its simplicity, efficiency, and minimal memory usage. Unlike the brute force approach, it avoids redundant work and doesn't require path storage. Compared to the iterative approach, it's more memory efficient and easier to reason about. While recursion does have the theoretical risk of stack overflow for extremely deep trees, this is rarely a concern due to practical problem constraints. Overall, the recursive solution strikes the best balance between clarity, performance, and resource usage, making it the most practical choice for this problem. The problem of finding the lowest common ancestor, or LCA, in a binary tree revolves around identifying the deepest node that serves as a common ancestor for two given nodes, P and Q. To clarify, the LCA is the lowest node in the tree that has both P and Q as descendants, or a node can be considered its own descendant. One straightforward way to solve this is the brute force approach. First, we perform a depth-first search to trace and store the path from the root to P, and then repeat for Q, saving these paths in two separate lists. Once we have these paths, we compare them index by index to find the last common node between them, which represents the LCA. However, this method requires extra space to store the paths and performs redundant traversals. To address this inefficiency, an optimized recursive approach can be used, allowing us to identify the LCA in a single traversal of the tree. In the optimized recursive approach, we define a function that takes the current node, root, along with the nodes P and Q as arguments. The base cases ensure the recursion terminates appropriately. If the current node is none, it returns none, indicating we've reached the end of a branch. Similarly, if the current node matches either P or Q, we return the current node because we've found one of the target nodes. From there, the function proceeds by recursively exploring both the left and right subtrees of the current node. Once both recursive calls are resolved, their results are combined. If both the left and right calls return non-none values, it means P and Q are located in different subtrees, making the current node their LCA. If only one of the calls returns a non-none value, it implies that both nodes lie within the same subtree, and we return that result. If neither call returns a valid result, we simply return none as neither P nor Q is present in this subtree. Ultimately, the function returns the LCA as the recursion unwinds. The recursive nature of this problem makes it especially well suited for a divide-and-conquer approach. By breaking the problem into smaller subproblems at each node, the algorithm naturally leverages recursion to determine whether the current node is the LCA or whether the search should continue in one of the subtrees. The base cases play a critical role here, ensuring that the recursion halts when it reaches a leaf node or finds one of the target nodes, P or Q. This solution is highly efficient because each node is visited only once, resulting in a time complexity of O(n), where n is the total number of nodes in the tree. Additionally, the function call stack itself serves as the data structure to backtrack and combine results, eliminating the need for extra storage. The recursive solution elegantly balances simplicity with optimality, making it a robust choice for this problem. This algorithm handles several edge cases seamlessly. For instance, if one node is an ancestor of the other, the algorithm correctly identifies the ancestor as the LCA because it encounters the ancestor node first during the traversal. Similarly, when both nodes are located in the same subtree, the algorithm naturally traverses only the relevant subtree, avoiding unnecessary computations. If the problem guarantees that both P and Q exist in the tree, we don't need to handle cases where they are absent. However, if such guarantees are not provided, additional checks could be added to verify their presence before proceeding. With these considerations, the algorithm ensures correctness and efficiency across a wide range of scenarios. Let's look at an example to see how the algorithm works in practice. Consider a binary tree with the root node 3 and 2 target nodes, P equals 5 and Q equals 1. Starting at the root, we recurse on both its left and right subtrees. In the left subtree, we reach node 5, which matches P, so we return node 5. In the right subtree, we reach node 1, which matches Q, so we return node 1. Back at the root, we now have none results from both the left and right recursive calls 5 and 1, respectively. This indicates that P and Q are in different subtrees of the root. Thus, the root node 3 is their LCA. The algorithm successfully determines the LCA with minimal computation, as it stops exploring branches once the relevant nodes are found. Analyzing the complexity, the time complexity of the algorithm is O(n), where n is the number of nodes in the tree. This is because the algorithm visits each node exactly once during the traversal. The space complexity is O(h), where h is the height of the tree. This accounts for the space used by the recursive call stack, which grows proportionally to the depth of the tree. In a balanced binary tree, h is logarithmic with respect to n, making the space complexity O log n. However, in the worst case of a skewed tree, the height could be equal to n, leading to a space complexity of O(n). Despite this, the recursive approach is efficient and well-suited for most practical scenarios involving binary trees. This implementation solves the lowest common ancestor of a binary tree problem by using a recursive depth-first search approach. Here's how it works step by step. 1. Base case, the function first checks if the current node, root, is none, or if it matches either of the target nodes, P or Q. If any of these conditions are met, the function immediately returns the current node. This serves as the stopping condition for our recursion. 2. Recursive search, the function then recursively searches for the target nodes in the left and right subtrees of the current node, storing the results in left and right respectively. 3. Determining the LCA, if both left and right are none, it means that P and Q are found in different subtrees of the current node. In this case, the current node is their lowest common ancestor, so we return it. For propagating results, if only one of left or right is none, it means both P and Q are located in the same subtree. The none value is returned up the recursion stack. If both are none, the function returns none, indicating that neither P nor Q exists in the subtree rooted at the current node. This algorithm effectively traverses the binary tree in a single depth-first search, making it efficient with a time complexity of O(n), where n is the number of nodes in the tree. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we start by defining the lowest common ancestor method, which takes 3 parameters, the root of the binary tree, and the 2 nodes, P and Q, for which we want to find the lowest common ancestor. The first step is the base case. If the current node, referred to as root, is null, or if it matches either P or Q, we simply return the current node. This is because null or a direct match means we've either reached the end of a branch or found one of the nodes we're looking for. Next, we make recursive calls to search both the left and right subtrees. By calling the same function on root.left and root.right, we effectively traverse the tree, looking for the nodes P and Q in both directions. The results of these recursive calls are stored in the variables left and right, representing the outcomes of the searches in the left and right subtrees, respectively. Once we have these results, we check if both left and right are not null. If this condition is true, it means that P and Q are found in different subtrees, and the current node, root, is their lowest common ancestor. If only one of the recursive calls returns a non-null value, it means that both P and Q are located in the same subtree. In this case, we return whichever of left or right is not null, as it points to the subtree containing both nodes. This ensures that the recursion continues correctly up the tree. Finally, we include the definition of the treenode class, which represents each node in the binary tree. It contains an integer value val and references to its left and right child nodes. This class is essential for constructing and navigating the binary tree used in this algorithm. With this implementation, we can efficiently determine the lowest common ancestor of two nodes in a binary tree using a recursive approach. In this first example, we're working with a simple binary tree where the root node is 3. The task is to find the lowest common ancestor of nodes 5 and 1. We start at the root node, which is 3, and check if it matches either of the target nodes, 5 or 1, or if it's null. Since none of these conditions are met, we proceed to search the left subtree, where the root is 5. At node 5, we find that it matches one of our target nodes, so we return node 5. Next, we go back to node 3 and explore the right subtree. Here, the root is 1, and since it matches the other target node, we return node 1. Now back at node 3, we observe that the left and right subtrees have returned non-null values, specifically nodes 5 and 1. This means that node 3 is the lowest common ancestor of nodes 5 and 1, so we return 3. In the second example, we're working with the same binary tree, but now the task is to find the lowest common ancestor of nodes 7 and 4. We again start at the root node, 3, and check if it matches either of the target nodes or if it's null. Since none of these conditions are true, we proceed to search the left subtree, where the root is now 5. At node 5, we first explore the left subtree, where the root is 6. Since node 6 is neither 7 nor 4, and has no children, it returns null. Back at node 5, we now search the right subtree, where the root is 2. At node 2, we explore its left subtree, where the root is 7. This matches one of our targets, so we return node 7. Next, we explore the right subtree of node 2, where the root is 4. This matches the other target node, so we return node 4. Back at node 2, we now see that both the left and right subtrees have returned non-null values, specifically nodes 7 and 4. This means that node 2 is the lowest common ancestor of nodes 7 and 4, so we return node 2. Returning to node 5, we pass node 2 up as the result of our left subtree search. Meanwhile, when we search the right subtree of node 3, where the root is 1, we find that it returns null since it doesn't contain either target node. Combining these results at node 3, we see that the left subtree returns node 2, while the right subtree returns null. Thus, node 2 is confirmed as the lowest common ancestor of nodes 7 and 4. In the third example, we're tasked with finding the lowest common ancestor of nodes 5 and 6. Starting at the root node 3, we check if it matches either of the target nodes or is null. Since none of these conditions are true, we move to the left subtree, where the root is 5. At node 5, we find that it matches one of our target nodes, so we return node 5 immediately, as it serves as the lowest common ancestor in cases where one target node is a direct ancestor of the other. Back at node 3, we pass node 5 up as the result of our left subtree search. Meanwhile, when we search the right subtree of node 3, where the root is 1, it returns null since it doesn't contain either target node. Combining these results at node 3, we see that the left subtree returns node 5, while the right subtree returns null. Thus, node 5 is confirmed as the lowest common ancestor of nodes 5 and 6. The time complexity of the recursive solution to the lowest common ancestor of a binary tree problem is O(n), where n represents the total number of nodes in the tree. This is because the algorithm relies on a depth-first search, or DFS, traversal, meaning it visits each node once in the worst-case scenario. For example, if the tree is highly skewed, or if nodes P and Q are both located at the deepest level, every node in the tree would need to be processed. At each node, the algorithm performs a constant amount of work checking base cases and combining results from the left and right subtrees, so the overall time complexity is proportional to the total number of nodes, giving O(n). Now, in the best-case scenario, if the node being evaluated early in the DFS is either P, Q, or their lowest common ancestor, the recursion may terminate much sooner. In this situation, only the nodes along the path from the root to that point are processed, giving a time complexity of O(h), where h is the height of the tree. However, in the worst-case scenario, which occurs in a skewed tree or when P and Q are at opposite ends, the traversal still requires visiting all nodes, making the complexity O(n). The space complexity of our solution is determined by the depth of the recursion stack during the DFS traversal. This depth corresponds to the height of the tree, making the space complexity O(h), where h is the tree's height. For a balanced binary tree, the height h is approximately log n, so the space complexity in such cases is O log n. However, if the tree is skewed, the height is equal to the total number of nodes n, leading to a space complexity of O, n. Each recursive call in the stack uses a constant amount of memory to store the function's arguments and local variables, so the total memory usage grows with the maximum depth of recursion. When we compare this to a naive or brute force approach, which involves storing the paths from the root to both P and Q, the recursive solution is clearly more efficient. The naive method adds space complexity of O, n, to store these paths, in addition to the O, n, time required to calculate them. In contrast, the recursive approach eliminates the need for extra storage and keeps the space usage limited to the recursion stack. To summarize, the time complexity of the algorithm is O, n, because, in the worst case, every node in the tree is visited exactly once, with a constant amount of work performed per node. The space complexity, on the other hand, is O, h, where h is the height of the tree. For a balanced tree, the height corresponds to log n, making the space complexity O, log n. In the case of a skewed tree, the height equals n, resulting in O, n, space complexity. Overall, the recursive approach strikes a balance between time efficiency and memory usage, making it optimal compared to the naive method. By avoiding any additional storage requirements like path arrays, it ensures that space usage is restricted to the recursion stack, while still maintaining a worst-case time complexity of O, n. When solving this problem, there are several common mistakes to watch out for. First, failing to account for edge cases is a frequent issue. For example, what happens if either P or Q is the root of the tree, or if they are the same node? These situations can easily be overlooked but must be handled explicitly in your code. Another challenge is inefficient traversal. If you end up redundantly traversing the same parts of the tree multiple times, your solution could degrade to O, n squared, complexity. To avoid this, you should aim for a single pass traversal wherever possible. Recursion, while powerful, also comes with its pitfalls. Forgetting to return the correct values or failing to terminate recursion properly can lead to stack overflow or incorrect results. It's also important to carefully check the problem's constraints. For instance, don't assume P and Q will always exist in the tree unless the problem explicitly guarantees it. Finally, avoid hard-coding values or making assumptions about the size of input data. Your solution should be robust, scalable, and able to handle a variety of tree structures without making arbitrary assumptions. In interviews, it's important to approach this problem methodically. Start by clarifying the problem requirements with your interviewer. For instance, is the tree a generic binary tree or a binary search tree? This distinction matters because for BSTs, you can leverage the property that values in the left subtree are smaller than the root, and values in the right subtree are larger. Next, recursion is often the most natural way to solve tree-based problems like this. Be sure to outline your base cases and recursive logic clearly, as it demonstrates your thought process. However, be prepared for trade-offs. If your interviewer prefers an iterative solution, such as to avoid recursion due to stack size limits, you should be ready to implement it using an explicit stack. Finally, always explain the time and space complexity of your solution. For example, a recursive approach typically runs in O, n, time, where n is the number of nodes, and it requires O, h, space for the recursion stack, where h is the height of the tree. This shows you understand the efficiency of your approach. This problem is closely related to several others on LeetCode, and understanding these can deepen your grasp of tree-related algorithms. For example, LeetCode 236, which we're discussing, finds the lowest common ancestor in a generic binary tree. LeetCode 235, on the other hand, focuses on the lowest common ancestor in a binary search tree. The constraints of a BST allow for a more optimized approach in that case. LeetCode 112, PathSum, is another related problem, as it also involves recursive traversal to determine if a specific condition is met in a tree path. Lastly, LeetCode 543, Diameter of Binary Tree, explores a distinct but related concept, where you calculate the longest path between any two nodes in the tree. Familiarity with these problems can provide a broader perspective and help you recognize patterns in tree algorithms. When it comes to alternative approaches, there are a few worth mentioning. A straightforward but less efficient method involves storing the paths from the root to nodes P and Q. Once you have these paths, you can compare them to find the last common node. However, this approach has higher space complexity because you need to store the full paths. A more efficient solution is the recursive single-pass approach. This leverages the insight that the lowest common ancestor is the node where one target is in the left subtree and the other in the right, or where one of the nodes is the root itself. This method only requires a single traversal of the tree, making it optimal in both time and space. Lastly, there's the iterative solution using parent pointers. Here, you build a parent-child relationship map using BFS or DFS, then trace the paths from P and Q back to their common ancestor. While this method avoids recursion, it's more space-intensive due to the additional storage for the parent mapping. Understanding these approaches allows you to adapt your solution based on constraints and preferences. Great job! We've successfully tackled the lowest common ancestor of a binary tree problem. We reviewed both brute force and optimized solutions, highlighting the importance of recursion and backtracking. Keep practicing, and don't forget to subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!